Hello and welcome to this video. We are going to talk about linked lists using structures in C++. So linked lists is an interesting topic, especially because the scalability that they offer over arrays. We know in C++ the arrays need to be defined beforehand, so we know that you need to know how long the array is going to be. Now granted, you can define a dynamic array where you can basically declare an array of any size, but you still need to know how long that array is going to be. So with an array, we are kind of limited with how many nodes or elements in the array we can have. So we need to know the size of the array. Now that's good for situations where we already know the size of the array or size of the elements that we're going to save in the storage in the memory, but sometimes we don't know that. So let's say I have an application where I may be needing one element, or I may be needing 100,000 elements. In those situations, because there's a maybe in there, the best way to go is to write a linked list. And because we're using structures as our data storage, our structure is going to look like this. So the structure is called node. This means each node is an object of type structure node. It has two data members. The first one is integer, it's called value. The other one is the pointer, node pointer. So what this essentially means is that next is pointing to the same node, same type of node. And we use this because a linked list is a list of connected nodes, and this next is what makes that connection happen. We'll see that in a bit. So this is what this looks like in the memory. You have the value part, and then you have a pointer part. This is the next pointer, and this is the value part. So the value is 100. Next pointer, well, when we create a new node, it points to nothing, so it points to null. This is one node. Now your linked list looks like this. We always have a root. We never lose our handle to the root. So root is always there, and your linked list is created by adding more nodes to your linked list. So in this particular case, I have three nodes, and the last node, the next pointer for the last node is null. So that's the indication that this is the last node in my linked list. Another important point to note is that linked lists are sequential access. So you always need to know where root is, and you start from there and you basically jump to the other nodes. When you reach, how do you know if you have reached the last node? Well, the next pointer is null. So if the next pointer is null, you know you are at the last node. So this is your linked list. And the reason why I was explaining linked list to be more scalable is that each one of these nodes resides somewhere in the memory randomly, so they don't have to be consecutive memory locations like arrays. Excuse me. So I can have 10 of these, or I can have 10,000 of these. As long as I have memory, my linked list should be okay. I can keep creating more nodes. So how do we actually create another node and link to this linked list? Well, the process is a simple few steps process, and I'm going to explain that just now. So the first thing that you need to do is to move the current pointer to the last node. So current pointer essentially is a pointer that points to root. Because we don't want to touch root or change the value of root, because if we do, we lose our linked list. We never touch root. Therefore, we create another variable. You can call it anything. I call it current, which points to the same node. So at this point, both root and current are pointing to the same node. So next, we move current to the last node. So we're going to add a new node to the end of this list. So first we have to reach the end of the list. It's sequential access, remember? So we move current to the last node. And I'm going to show you when I write this code how we move current to the last node. We basically keep jumping forward. So jump from here to here, jump from here to here, and there we are. once current is pointing to the last node, now we create a new node by saying node pointer temp equals to new node. So this is a temporary pointer, temporary node, and this is what it looks like. Just like a regular node, it's a regular node. It's just that it's called temp. So now that the node is created, we must assign it the value that we want to assign. So let's say we want to assign it a value 20. We just go ahead and assign it that value. You can take this value from the user and just assign that value to temp.value. Next up, we make next null. So because this is going to be the last node in our linked list, its next variable, next pointer, must be pointed to null, and that's what we did here. So now next is pointed to null. Our node is kind of complete, just one step remaining, and that step is I have to link my new node, this blue one, to my linked list. And for that, I need to point current's next pointer to temp, and that's what I'm going to do next. So current.next equals to temp. So current.next is temp, and now I have actually created a linked list where my current.next is temp. I can keep creating as many nodes as possible as I want using this, and yeah, so this is your linked list. Next up, we're going to program this. So now we create our linked list. We write some code to create the linked list. I've opened the Visual Studio project, and I'm going to start by writing my structure. As I explained earlier, and my struct is called node. It has an integer variable called value, which will hold the value for the node, and it has a pointer of type node, so it points to node. Next, I'm going to create a linked list. So the first step for creating a linked list is node root equals to new node. So that's my first node, node current. So node current equals to new node, and then I'm going to say current equals to root. As I said, we don't touch root, so we will use current all along. Then I'm going to create a new variable called input val, and I'm going to make it 0. This is going to hold the value that the user inputs. So the linked list is going to be populated by user inputs. Whatever value the user inputs, a new node will be created, and that new node will be assigned that value. Next up, I'm going to ask the user to enter a number, and I'm going to cin that number into input value. Then I'm going to create my root. So for that, I create a new node, call it temp. So node pointer temp equals to new node, temp dot value equals to input value. And since this is the only node in the linked list right now, temp.next is null. The only node in the last node, so temp.next in either case is null. Root equals to temp, because root is the only node, root must be pointing to this node, and because root is pointing to this node for start, current also must point to the same node because it's the only node. So this is kind of some logistics. The first node is created. After this, we move on and we build the rest of the linked list. So build rest of the linked list, and we do that using a do while loop, and do while loop because the first time we just want to create a node, and after that we decide whether we want to create more nodes or not. So it's going to be based on user input. So when a user enters a 0, we exit. That's the last node. Not even the last node. When a user enters a 0, we don't create a node when the user enters a 0. That is not a valid node. So while input value is not equal to 0, just keep making nodes. So cout again, ask the user to enter a number, and cin that number goes into input value. And here I'm going to check if input value is equal to 0. What should we do? Simply break out of the while loop. Break. Otherwise, if it's not, then create a new node called temp, just like we've done before. Temp.value is equal to input value, and temp.next equals to null, since this is going to be the last node in the linked list, or this may be the last node in the list, we don't know, but each new node added at the end of the linked list has the next pointer null. That's how we stop if this was to be the last node in the linked list. And the current node must now point towards the newly created node called temp, and let's move current forward to temp. So current is now pointing to the last node in the linked list. That's it. We've created our linked list. Next up, I'm going to write a function called print linked list. So it's a void function, print linked list. It takes in a node pointer called root, and we need to do that because we have to provide a root address to the linked list. So whenever we call these functions, all the functions that I'm going to write right now, we'll always pass the root. So print linked list works in a very similar way. So we first create a new node pointer called current and point it to root. Then we say for cosmetics cout list. It starts here. Then we put a do while loop, and how far are we printing? We are printing until current.next is not equal to null. Okay, so this creates a potential problem for us as well. We're going to mitigate that problem by writing an if statement inside this do while loop. You don't have to do it, but I'm going to do it because I don't want to complicate it at this point. In future programs that we're going to learn about linked list, I'm going to actually write much smaller amount of code because you would have learned it by that time. So when you are inside this do while loop, the first thing you want to do is you want to go ahead and print the current value, current.value. And we're assuming there's at least one node. In this current implementation, there's always be root at least, so we can just print that without the fear of trying to print something that doesn't exist. So we do this, and then we move forward. So we say current equals to current dot next. If you think this is too small, let me just increase the font size here. Okay, so current is equal to current. The problem is you've printed, let's say you've printed the second last node and you've moved current to current dot next. You're already at the last node, and for the last node current dot next is null, so you will skip printing the last node. For this, I'm just going to put an if statement. If current dot next is equal to null, which means you were at the second last node before, you printed the second last node, I'm going to ask this do while loop to print the last node as well with the second last node. Obviously your implementation can vary, and that would be correct as well. I'm just trying to keep things extremely simple here. Cout just cosmetics, ending bracket for the list, and that's it. So let's go ahead and test our print function. That we'll do here. So I'm going to call the print function, but before that I need to go and write the prototype for this function, for the main function. So that's the prototype for the function. I'm going to call this function here print linked list. Is that the name? Oh, sorry. Print print. Okay, so let's call print here. So print linked list, and we pass in root. Okay, let's see how this goes. So 1, 2, 3, 4, 5. It prints. We are good. So we've added. We've created a linked list. We've added few nodes, and the next step is obviously to create more nodes. So let's add a function to add a new node to this linked list. Obviously, you don't want to limit yourself to adding the nodes only when creating a linked list. You want to add, maybe you want the ability to add nodes once you're done creating the linked list for the first time. So I'm going to call a function called add node, and this obviously is also going to take root, and I'm going to provide it with the value for that the user wants to add. So okay, so the first thing we do here is, again, node current equals to root. So we point current to root, we don't touch root, and then we make sure that current is pointing to the end of the linked list. So for that we need to put a do while loop here. Do while, and you guessed it right, current dot next, while current dot next is not equal to null. Keep moving forward. Current equals to current dot next. So you keep moving forward until you reach the end of the list. By the time you're done with this while loop, you will be at the end of the list. At this point, we're going to start and add a new list, a new node. So node pointer temp equals to new node. So now you create a new node, you assign it that value. So temp dot value equals to val is the value that the user provided. Next, you make the next pointer to temp a null, because this now is the last node in the linked list. The next pointer has to be null, and then you say current, which was earlier the last node, no longer the last node. Current dot next is temp. So temp is now the last node, current is now the second last node. But before we leave, we you don't really have to do that. Okay, so let's say current equals to current dot next. You don't really need to write this line. This is kind of optional, but if you wonder why it's not there, you can just put it there. It doesn't really matter at this point. But okay, so we've added a new node. Let's go ahead and see how we have done. So I'm going to say add node, and I'm going to pass root, and I'm going to pass in the value for the new node, and I'm going to print the updated linked list as well. And where is the linked list? So I'm just going to put an end line here, so that each time the linked list is printed, it's printed in a new line. So what's up? Okay, I don't have a prototype for this function yet. So void add node pointer, and an integer. So there's my prototype. Let's try to run it now. Okay, 1, 2, 3, 4, 5, 0, and sure enough, it added the last node. Now you may want to add a new node, not just at the end of the linked list, but maybe somewhere in the middle. Next up, we're going to write a function which adds a new node between existing nodes. So we call that function, it's a void function, add node between. Very basic name. Again, we pass in a root pointer, and here I'm going to pass a, which is the value of the first node, b, and then val. So I want to add a new node with value val between a and b. That's the idea here. So again, create a new node called current and make it point to root so that we don't touch root. And then in a do while loop, I'm going to do all the magic here. So while, well, it's not really magic, it's known. So while current dot next is not equal to null, we keep doing this. And what we're doing is we're saying if, and now notice this, if current dot next is equal to A and current dot next dot value is equal to B. And I'm sorry, I meant current dot value here, not current dot next. So if current dot value is A and current dot next dot value is B. Now we know that current is a node, but interestingly, current.next is also a node. This is the second node in the linked list, or the node after the current node, depending on where you are in the linked list at a given point. So if these two values match, then we want to create a new node. So let's go ahead and create a new node. How do we create a new node? We create a temp new node. We say temp.value is equal to val, and so now you're creating a node between two nodes. So the pointer situation, which was here, will be a little different. Let's see how it will be. So you assign that value, and then you say temp.next is actually current.next. So what current was pointing to earlier, temp is pointing to now. Okay, so current is kind of in the back end now. Temp has intervened between current and current.next. So earlier current was pointing to current.next, now temp is pointing to current.next. And to make sure that the linked list is joined, we want to make sure that current.next is pointing to temp as well. Okay, but what if this match is not happening? What if we don't have a match here? If we don't have a match here, then keep moving forward in the linked list until you find a match. So else current equals to current dot next, and that's it. Yeah, that's it. So this is what we can use to add a new node between nodes. Let's go ahead and write a prototype for this on the top. So void add node between, node pointer, an integer, another integer, another integer, and that's the prototype. Let's go and try this out. So I'm going to call this function a node between. I'm going to pass in root, first parameter, and then I'm going to add two nodes between 2 and 3. So 2, 3, and the new node's value is 4. So all I need to do is just make sure that there are two consecutive nodes in the linked list with the values 2 and 3. So that's what I'm going to do. Okay, let's hope this runs. Okay, 1, 2, 3. So these are the two nodes that will be intervened by our new node, and sure enough 44 is placed between 2 and 3. Okay, so that's the second situation with add. What if you want to add a new node at the beginning of the linked list, which means replacing root? So next we're going to do that. I'm going to write a new function, and I'm going to call it, it's a void function, add node beginning. Begin. Again, node pointer, and because it's the beginning, I just need an integer value. I don't need anything else. In other words, I'm adding a new node before the root node. I already know root because this is root right here, so I don't need to know anything else about anything else. All I need is the root address, and all I need is the value. So again, not touching root, current equals to root, and create a new node, and notice we don't need to reach the point where we want to add a new node. We know we want to add a new node before the root node, so that's what we're going to do. So node pointer temp equals to new node, temp dot value is equal to val, and notice the pointers now. So temp dot value is val. Where do you think temp is pointing? Because temp comes before the root node, temp is pointing to root. Okay, and interestingly, we don't even need the current variable here, I suppose. If this is what we're doing, then we don't need the current variable. Okay, so temp.next is root. Okay, that sounds good. Temp.next is root. So temp points to root. But now we have a new root. So root equals to temp. This finishes this. But how will the main function know that we have changed root? Remember, whenever you change root, you have to inform everybody else. And here we have to inform the main function. So we must return root, which means the return type is not void. It's going to be a node pointer. So we're going to return a node pointer. In other words, we are going to return the new root. So return new root. And so I'm going to write the prototype for this. It's a node pointer. That's the type of the function. Add node begin node pointer and an integer. So that does it. But because we are returning now, we need to use this function carefully, because this function is going to hold a new value. So let's say that we call this function right here add node begin, and we pass in root, and we say the new value is 90. Okay, but because this function is returning, and what is it returning? It's returning the new root. We simply directly save it to new root, and this should basically do it. Let's see if we can print this. Print after adding a new root. So at the end of this, we should expect 90 to be the first value in the linked list. So 1, 2, 3, 4, 5, 0, and sure enough, we have 90 in the linked list. Remember, we added 44 between 2 and 3. We already added 23 at the end of the link, so we're kind of gone full circle. We have added a new node at the end of the list, added a new node between existing nodes, adding a new node at the beginning. So add node is complete. And I'm thinking, should we just go ahead and do the complete, do the delete node as well? I think we should just write the delete node function right here as well. So now I'm going to explain how you delete a node, and I'm going to just write a delete function which has all of the functionality just in one function. So delete node. Delete node obviously takes in root as well, root pointer, and it takes in a value that you want to delete, node value that you want to delete. So first things first, create a current pointer and point it to root so that we don't mess with the root unless we have to, and we'll see why. Okay, so next I'm going to, so the first thing I'm going to do is I'm going to write the if statement. So in other words, I'm going to say if the node that you're trying to delete is the current node, or if root is the only node in the linked list, in this particular code situation we cannot delete root. So that's what I'm going to check, the first thing. So if current dot next is not equal to null, if it's equal to null, then you're going to simply say else. You're going to say cout sorry, cannot delete root, and that you should understand that this is purely because we have written the code like this. In the next video, I'm going to explain how to create linked lists using classes, and there you can see that you can easily delete the root as well. So as long as root is not the only node, we can go ahead. The first thing I'm going to check is if current dot value is equal to val, and current dot next is not equal to null. Now, although you've already checked for current.next not being not equal to null, this is kind of redundant. If you don't want to do it, don't do it. So if current.next is not equal to null and current.value as well, this means this is root. This means root needs to be deleted. So what do we do in a linked list when we delete root? We do nothing more than calling the second node root, and that's all that we do. So current, remember, is pointing to root, so we're going to say current equals to current.next. So current node now points to the new root, and we must return the new root to the main function. Remember the root, inform everybody if you change root. So return current, or you can say, yeah, just say return current. That should be okay. Return current. And obviously, because the function is void, we cannot do that, so we'll make it node pointer. This function returns node pointer. We basically lose the handle to the root, we move current to the second node, and we just return the address of that second node. So that's the first situation. If this is not the case, if your first node is not the value, or it's not null, you go into the else loop and you say, if this is not the case, then you say you declare two more variables. So I'm going to declare a node pointer before deleted. So this is interesting because after deleted, well, I don't really need after deleted, so let's just stick with before deleted. So before deleted is when you have to delete a node somewhere in between. You want to keep in handle to the list. So if this is not true, then you say that before deleted is equal to current and move current forward. I hope this is intuitive. If it's not, you can ask questions in the comment section below. Okay, so move to second node. So if this is not the case, move to second node, and second node onwards, the deletion situation is different. So what we did right here is we handled the root here. Now we're going to handle second node onwards. So second node onwards. If it was the new root that needed to be deleted, our function just returns from here and nothing else executes. But if it's not the node, then second node onwards, we write a do while loop. So do inside the while, and here I'm just going to say while true because I want to terminate it when I want to terminate it. So while true means it will just keep running. Sometimes it's not a bad idea, but sometimes if you really know what you're doing, it should be okay. So if the first thing that you want to check, if current dot value is equal to val and current dot next is not equal to null. Now remember, you're not at the root anymore, you're at the second node, and you want to check if the second node is the last node. So if this is the case, then after okay, before deleted, I think I need another one here called after deleted. So these are the two variables that I'm going to use. So then you say after deleted is equal to current.next. So you're just trying to hold on to both ends and insert a new node in, delete the node in the middle. That's what you're doing. And we create these variables, these pointers, so that we don't lose any handle. If we lose a handle to rest of the linked list, then the rest of the linked list is gone. We don't want that. So after deleted points to the next node from current. And remember, current is the node that you want to delete. So next, before deleted is dot next is equal to after deleted. So we've kind of removed current. Notice what we have done here. Current was before deleted, okay, and then we moved current. So before deleted pointed to old current. So before deleted was kind. So this was the situation. Let me explain the situation here. So you had before deleted pointing to current pointing to after deleted. This is what's going on, okay, and we are removing current by saying that before deleted dot next is equal to after deleted. So this should be simple. Next, you can simply just return root. Root doesn't change, just return root because you have to return something, or you can have at the end just return root from here. It's up to you. Okay, so if this is not the case, then the second situation in this if statement is else if current is the value and current.next is null, which means it's the last node. So if current dot value is equal to val and current dot next is in fact null. If current dot next is null, then our life is very simple because we don't have to worry about a lot of things. So in that case, before deleted dot next is equal to null, and that's it. And if you want to, you can just return root from here again and be done with it. If that is not the case, the third situation is that none of this works, so you move to the next node. Else before deleted is equal to current and current equals to current.next. So we keep our before deleted updated. After deleted is only updated when needed, but we always keep before deleted updated. And this is it. So yeah, in this case you can simply just say return RT, which means that even if you don't return RT here, your root address still gets returned. So now let's go ahead and try to run this. So I'm going to copy this and write the prototype. There's an integer, there's a node pointer, it's called node delete, and the return type is node pointer. So let's try to call this delete node. Okay, so notice that the last time we added a new node was 90, and now I'm going to attempt to delete 90. So I'm going to say root equals to delete node, and what that means is that we delete a node. Where is it? Delete node. We pass in root. Do we pass in root? Yes, we pass in root, and we say 90. So 90 is the node that we're going to delete, which means we're deleting root. And we're going to just kind of work systematically and see if all of these situations work. So 90, 2, 3, 4. Good. So 90 is deleted. Very nice. Okay, next up, we're going to say that delete the last node. So last node is, I believe, 23. So let's see if we can delete 23. 1, 2, 3, 4, 5. Nope. 23. Okay, so so delete is kind of messing this up. Let's look at delete. Okay, so I just figured it was a simple problem. I was not using the comparison operator. I'm just using the assignment operator. This is an if statement. I need a comparison operator. So this was the problem, yeah, this solves it. So let's try and run this again and see if it can delete the last node. So 23 is the last node in the linked list. let's see, 1 2 3 4 0. So sure enough, we can delete the last node, and now I'm going to attempt to delete a middle node. So I'm going to say 44. So 44. Okay, 1 2 3 4, and 44 is gone. So yeah, there you go. We've already tested the root node. So just going over the delete function once again, we first make sure that it's not the root that the user wants to delete. That would be the situation when root is the only node. We cannot delete that in this particular situation. Next up, if the root needs to be deleted and there are other nodes in the linked list, then you simply point root to the second node in the linked list and just return the new root. And if that is not the case, then you keep moving forward and make sure that before deleted always points to a node, one node before the current node, because we will need that handle when we delete a node which is in between two nodes, which is this situation. So if current node is the value and the next node is not null, this means this root second node onwards is somewhere in between the linked list. So after deleted is current.next, and before deleted.next is after deleted. So these two pointers we use for this. Since we are not changing root, we just delete, we just return the root that was passed into the function. This is where the problem was with this comparison operator. So if you're deleting the last node, it's really simple. Before deleted is already pointing one node before the current node. So current node is what you want to delete. So just say before deleted.next is null, current is gone. You can also optionally just delete current as well, just to save memory, release memory back to the operating system. If none of these is the case, then you keep moving forward, but making sure along the way that you keep track of before deleted and current. So before deleted always points one node before the current. So that's the basic rule for this particular implementation. Obviously, you'll find many different implementations online. The idea here is to make sure that you understand pointers, and this was the most basic implementation of a linked list. I didn't use any special code shortening techniques, no refactoring or anything like that. Just simple code. If a code and if you were looking at the linked list for the first time, I think this is pretty useful that way. So if you found this useful, please hit the like button, subscribe to the channel. More videos coming soon about interesting topics like this in C++. Thank you. Bye.